Hey everyone, this is Brian. Welcome to week 5 of CSC 143. We're almost halfway through the quarter. It is exam week for this class, and on Wednesday you're going to have your first out of 2 total exams you'll be having for this course. Exam 1 is going to take place entirely online. It's going to be like a Canvas quiz, but it'd probably take you about 2 hours to do rather than just 5 minutes. However, you'll also get access to your notes and the lectures and whatever course materials you'd like to access. It will be an open note, open book exam. You're going to have actually plenty of time to take this exam as well. When I drop the exam on Wednesday, you'll have pretty much at least several days to take the exam and turn it in. And there's actually not going to be a time limit on the exam itself, so you could technically start on Wednesday, wait and study for the rest of the week, and then answer the questions right before the due date. And again, you'll have at least a couple days to finish it, so you shouldn't be rushed for time or in a rush to study either. I want to make sure you have all the resources necessary to take the exam. And in today's video, we're going to go over some exam questions that you might be seeing as some examples. Before you actually watch today's content, I really encourage you to download the sample test that I've posted on Piazza. Try taking it on your own. It should take you about maybe 30 minutes to an hour. And see if you can do it actually without accessing notes, without accessing lecture videos. And that'll kind of give you a baseline estimate for how your knowledge is so far for this class. Then watch this video, see if your answers match up with my answers, and see what you need to focus on as far as studying goes, so then you'll be ready for the actual exam itself. Again, I wouldn't worry about the exam that much. The solutions to the exam problems are always going to be something that came out of the class itself. It's not going to be something that is totally made up or out of left field. What I don't want you to do for this exam, though, is take content outside of this class from third parties through like Google searches. Because you think you can find the perfect answer to copy and paste into the exam. That is not really what I'm looking for. What tends to happen when that happens is that I'll get weird answers for these questions that I'm trying to ask that are technically true, but actually not really answering the question that's being asked here. So keep in mind that everything that I do ask you on the upcoming exam is going to be based on something that we've learned so far. And I really encourage you just to go back to the lecture videos or go back into your own IDE, your own little sandbox environment to try running the code that you might be proposing to submit on the exam, just to make sure it's right. Okay, that's the big announcement. Before we get started onto the review video, I do want to talk quickly about the reading that I had to do last week, the I in the solid principles, the interface segregation principle. And interface segregation principle tells us that clients should not be forced to depend on interfaces they do not use. Let's break that down. We know what an interface is. It's essentially a contract that says, okay, if you're going to implement my interface, you are obligated to have these particular method implementations. That way, any clients of this class that you're implementing with can view that class instance as an instance of this interface. Several examples we've seen so far include the range and range iterator, which of course implement the iterable and iterator interfaces. We've seen the array list and how that's a collection type as well as a list type, which gives it certain methods that the Java single library is going to guarantee. And for the interface segregation principle in particular, it's discouraging us from having a super bloated interface that has a ton of stuff for the sake of fulfilling a whole bunch of client obligations. One particular interface that we've actually seen that kind of violates this principle is this range and range iterator that we wrote in Project Zero. If you remember, in Project Zero, I had you write range, which was an iterable type, so that we could iterate over a range. It's just a range of numbers, using that for each loop. And then the range iterator, which is the actual vehicle for performing the iteration. It's the thing that keeps track of the current state of the iteration. It has that next method that retrieves the next value. It has that has next method that indicates whether or not there is a next value, and so forth. If you remember, one of the methods that I had you do for range iterator was remove. And the idea behind a remove method on an iterator is that while you're iterating through a list or some other iterable type, if you invoke the remove method on the iterator, it removes the element from the list, or whatever is being iterated over. And the nice thing about having this remove method be available in the interface is that it means that for classes that do implement the remove method, you're allowed to not only iterate over the elements within the list or whatever structure is being iterated over, but also remove elements during iteration. Now, when I had you implement the range iterator, I actually told you to throw an exception when the remove method got called. Because it doesn't actually make any sense to remove a number from a range. If I have a range from 0 to 5 inclusive, and I am iterating over 0 to 5 and I'm on 2 and I call remove, that doesn't make any sense, right? Like the number 2 can't be physically removed from the numbers that belong between 0 and 5. So I had to throw an exception. I had to throw a not implemented exception, I think. And the reason I had to do this is because this is one way of indicating to potential clients of the range iterator that this method is not available. I'm not going to make this be something you can call, and if you do try and call it, it'll throw an exception and your program will crash. But there is a big concern with this approach, which is that throwing an exception is a runtime error. It's not a compile time error. Remember that interfaces are going to obligate clients to implement whatever abstract methods they have declared. If they don't, it's a compile time error. But they can get around it by using this trick that we just did, which is throwing an exception as an implementation. And that becomes a runtime error. So now in the future, technically, somebody could use your range iterator class. They could assume that all the methods next, has next, and remove are available, and they can compile the program. It'll compile, it'll run, but the moment they try to call remove, it'll crash. And that's bad, right? We want to prefer compile time errors over runtime errors so that we can circumvent whatever issues that we are having with our program in advance of actually releasing it to our clients. In this way of throwing an exception for the remove method for the range iterator, we are seeing how we violate this interface segregation principle because the range iterator is forced to depend on a remove method that it does not use. We see how the iterator interface is a bit too broad for the application that we're trying to use with it, such that we're actually introducing a potential runtime error and conflict with this range iterator that is, for all intents and purposes, an iterator, but is missing a core component of what the iterator interface itself is demanding. One way we could fix this in Java is if we split up the iterator interfaces into multiple kinds of iterators. Maybe something like a read-only iterator that's only capable of doing next and has next, as well as a iterator that can remove, or maybe something with a better name, that is an extension of the read-only iterator, but also has write capabilities and capabilities to remove or replace. That way, when we have iterators like these range iterators that are mostly just like static constant iterations, they don't have to necessarily depend on these extra methods that they don't want to implement and introduce runtime errors for. Okay, that's a lot of talking from me. Again, get ready for your exam. I wouldn't worry about it too much, and do refer to the notes. I really encourage you to do so you can do well on the exam and come up with the right responses to all the questions. Okay, thanks for listening. Enjoy the video. Hey everyone, this is Brian, recording a video review of the solutions to the sample exam 1 problems. If you haven't seen these sample problems yet, please stop this video, go check out the exam 1 details post, and download these questions so that you can try to fill out them on your own as a way of exercising your knowledge before the exam. Let's go ahead and dive in. We start out with these 3 true or false questions. The first one asks, in test-driven development, tests are written after implementation is written. This is, of course, the opposite of the case. We talked about how test-driven development encourages us to write tests first so that we can have a concrete program specification and interface, and then we're going to evaluate the correctness of our implementation using these tests that we've written in advance. So, tests are not written after implementation in test-driven development, they're written before. This one's definitely false. The second one says, the memory location of Java object instances on the heap is always arranged in the same order as the objects were constructed using the new keyword. This is, of course, not the case if you think about how objects are being allocated and garbage collected as we construct them. Over time, we're going to be building a whole bunch of objects using the new keyword, whether these are nodes in a linked list or contiguous chunks of arrays for the array list, and then objects are going to be freed over time as we lose access to those instances. The outcome of this is that the heap, which is the underlying memory structure, which stores all these live instances, is going to have several filled spaces and several gaps. As gaps appear, Java is going to reuse those gaps in the memory with new instances that we build. We can't just physically continue to put our instances one after another because we need to free up the old space that we're no longer using. So this is definitely false. Another simple way to think about it is, if this was always true, then we would essentially have unlimited memory if we just kept calling new, because all of our memory addresses will continue to grow in a linear fashion. The third one here, Java is passed by value, arguments and return types are copied. Return values are copied. Yes, this is very much the case. It will always be the case that Java is passed by value. It is also the case that Java is a language that uses references. Every time we see a variable declaration, whether it be in an argument or the body of a function, it's actually a reference to a live instance. So even though the copy operation may be physically costly, if we're copying a lot of bytes, we're actually just copying references around, which are just pointers underneath, which are pretty cheap to use. Okay, in this next section, I give you a couple of blocks of code, class A and class B, which extends A. I give you two methods that override the toString implementation, where class A overrides object's toString and class B overrides A's toString. And I ask you some polymorphism questions to see the effect of referencing instances of these objects from different perspectives. I build a new A instance with 1 inside and a new B instance with 2 inside, and then I replace the A reference with whatever B was referencing. Of course, this is okay because B's are A's, B extends A, so I'm permitted to view a B instance from the perspective of an A reference. Then I ask you what happens when we call toString on the A reference and toString on the B reference. When I invoke toString on the A reference, what Java is going to do, thanks to polymorphism, is it's going to go find the underlying implementation for the underlying instance and invoke the most specific implementation it can find. The outcome is that, despite the fact that we are viewing this B instance from the perspective of an A reference, it's actually going to go about invoking B's toString, which is why we get B2 on the right side here. The second example, with B's toString call, is much more straightforward. B is indeed a reference to a B instance, so I just invoke B's toString and get B2 as well. On the next line, I construct a brand new B instance with 3 inside and try to cast it to an A. This is a valid cast because it's always safe to cast up. I can always view a specific child instance from the perspective of a parent and from a parent reference. However, it is potentially dangerous to cast down. I can't always guarantee that a parent reference is being fulfilled by a child instance. Anyway, in this case, I'm trying to assign this B of 3 into the space where an A belongs, which is of course okay, and then I try to invoke A's toString again. Once again, thanks to polymorphism, Java is going to go find the most specific implementation available on this child class. So here, despite the fact that we cast it to an A reference, this is really still a B underneath. And it's going to go find B's toString method and print out B of 3. On the right hand side here, the B reference never gets updated from its previous reference, which was this new B of 2 we constructed up here. So we get B2 on the way out. I think this is a pretty straightforward thing to understand, that Java is always going to go find that specific implementation, regardless of how we view the object and the reference we're using, the type of the reference that we're using to view it. However, it's pretty easy to get confused in these more specific cases where there's casting involved, or there's assignment involved. Just keep it in mind that thanks to polymorphism, we're always going to get this most specific implementation that is available to the child class. Okay, next I ask you to list 3 differences between abstract classes and interfaces. We've talked about how these two things are very similar. They both involve abstraction, quite literally within a programming language, that enforces a child class to come along and provide concrete implementation for these abstract entities. There are some key differences though between these two. For abstract classes are indeed classes. They can have things that classes have, including properties and implementation. For the sake of this class, we're going to say that interfaces cannot do those things. Interfaces are just a list of method declarations, method signatures that child classes are obligated to fulfill. So that'll be my first point. Abstract classes can contain implementation, interfaces cannot. The second big point is that Java is a single inheritance language, which means a class can only extend one other class, but it can implement as many interfaces as it would like, mix and match. This gives an additional flexibility to interfaces that abstract classes don't necessarily have. So my second point will be, a class can extend only one class, but can implement any number of interfaces. The third point is a bit more complicated. It's this idea of abstract classes living in a hierarchy. In project 1, I had you implement building class that was extended by a store class that was extended by a restaurant class, and so forth. We can have multiple layers of abstract classes extending one another, and they live within the hierarchy of this world that we're building. Interfaces kind of live up and out in the air, in the cloud, and not necessarily attached to one of these hierarchies. We didn't really talk about interface interface extension. It is something that can be done, but these interfaces are just perhaps extensions of one another, but not necessarily enforceably attached to an existing class hierarchy like we would see with the world classes that we built and maybe the list like abstract classes in the Java standard library. So my third point here is that abstract classes live in that class hierarchy, interfaces do not. Abstract classes conform to the same sort of casting rules that we saw, where you can always safely cast up but can't always cast down. Interfaces, we're going to say that they just obligate certain behaviors of child classes, but they're not going to affect the hierarchy of child and parent relationships. Okay, on the next page, I give you a very basic implementation of this point, which seems to be a container of two coordinates, x and y. And on the right, I give you a point 3D, which extends point, which adds an additional z field, which of course is the point, but in 3 dimensions. And what I ask you to do is write an implementation for this equals method that compares the state of two instances using the instance of keyword. Remember that with equals, we are doing a value-wise equality. This is in contrast to the double equals operator in Java, which performs a reference equality, which enforces physical equality. This equals method here is going to go validate that all the internal fields between the two instances are the same, and it's going to permit those things to be equal regardless of their physical location in memory. That's going to permit us to evaluate whether or not two different instances are equal to one another by their internal state. Furthermore, when I ask you to use the instance of keyword, you should be thinking about the implications of parent and child relationships. Instance of is going to permit parent classes to equal child classes. This is because child classes are indeed instance of a parent class. This is in contrast to the getClass method, which you talked about as an alternative to this keyword, which is going to enforce two classes have strict class equality. This is not going to permit parent classes to equal child classes because there is that strict class equality, but it also does kind of violate that Liskov substitution principle, where we expect child classes to be able to fulfill the obligations of a parent class and without to be used as an instance of those parent classes without knowledge. Here's my solution. You should, of course, always start out with those basic guard statements, the null check, which if the object being passed in is null, return false, the self check, if the object being passed in is the same as this one, return true, and of course this instance of check, where if the object being passed in is not an instance of the point, we want to return false. Then we want to do a cast of the object being passed in to a point type, which is something we do have to do because the method signature of equals obligates us to do so. The reference that's being passed in is an object type, not a point type, so we do have to cast it. We know it's a safe cast to do because we already passed this guard statement for the instance of check. And then we go ahead and validate the equality of the internal fields. Here, because x and y are both primitive types, they're both primitive integers, I can use the double equal operator to compare those primitive types by their values. If point involved object types, object references as x and y, we would of course want to sort of recursively invoke the equals method upon each of these fields, such that we would delegate the equals validation to the underlying types that x and y would be. On this third page here, I give you a class hierarchy that involves abstraction. Starting from the upper left, we see that we have an abstract class shape with an abstract double area method. This is, of course, just a method declaration, which means any class that extends shape is obligated to implement the area method. On the right, I have a public interface named that has a public string getName method and a setName method declaration. Again, just like with the abstract class, the interface method declarations are going to be abstract, and any class that implements this interface is going to have a concrete implementation available for those methods. Now on the lower left, we see this public class rectangle that extends shape and implements named. this should automatically tell you that rectangle must provide concrete implementation for the area method, the getName method, and the setName method in these abstract parent entities that it chooses to extend. Inside the body of the rectangle, I have a width and the height, and a simple constructor. Next, on the right here, I see a public class square that is going to just extend the rectangle. By nature of the square extending rectangle, squares are rectangles, but also squares become shapes and named. This is because the rectangle class will have been obligated to implement those abstract entities already, so square is just going to get them for free by nature of inheritance. I ask you about the implication of abstraction by asking you to write the minimum amount of code required for these classes to compile. I don't want you to provide much implementation if it's required. Method stubs are okay, so give me empty braces or just return null. For rectangle, I know I have 3 abstract methods I need to implement: area, getName, and setName. For area, all I have to do is return a double, so the simplest thing is to return 0.0. You can also return width times height if you're feeling generous there, but 0.0 is fine because I asked you just to return a stub implementation. For getName, the empty string works as that, and for setName, because it's a void, I don't have to return anything, but I do have to have an implementation here, so just use the empty curly braces. Next, I ask you to write the minimum amount of code for square to compile, assuming that rectangle compiles correctly. When we assume that rectangle compiles correctly, we assume that it already provides concrete implementation details for these abstract entities, in which case, square doesn't actually have to do anything, which is great. One little detail, though, that we may have missed is that square is a child of rectangle, and rectangle has its own constructor. Remember that with inheritance, the only thing that doesn't really get inherited from the parent is the constructor. So for square, we do actually have to write our own constructor here. We don't just get it for free. Inside the body of square, I go ahead and declare a default empty constructor and call super as 0,0. You do also have to call the super method in order to invoke the parent's constructor inside the body of the child constructor. Okay, that's actually pretty straightforward, I think. Be careful not to forget the obligations that these classes have and the implications of child classes when they extend these parent classes. Okay, on the last page here, we have a linked list problem. I give you a node class, which simply stores a payload and a next reference to another node. Then I have a linked list wrapper, which has a head node and a tail node. And what I'd like you to do is implement this get method here, which is going to go return the underlying payload value of the node at the index. I give you some simple rules. You can assume that index is non-negative, but if it exceeds the length of the list, throw an index out of bounds exception. I'm not going to give you access to a size method, and I don't want you to use additional data structures. That would be kind of silly to use an array list here in the body of a linked list, so please don't do that. I also don't want you to mutate the list at all, so don't reassign head or tail. Before I dive into the implementation, I do want you to think about what you would have to do to fulfill the body of this method. With get, we don't have the convenience of fast indexing like we saw in array list. We do have to walk the elements of the list to reach the index that we're trying to get to. The head element is of course 0, index 0, and without the size method, we have to still walk the list to determine if the index is within bounds. Walking the list is not terribly complicated. It's just a matter of having reference to the head and then replacing it with head.next until we reach the node we're trying to look for. But this is actually presents quite a challenge to some people because it involves reference manipulation to a degree that you would not see with the array list. So I do want you to be really comfortable with this implementation, and this should be something that you can just do naturally. Okay, let's go ahead and dive into this get method. We'll start out with some basic declarations. We need a counter to represent the current index we're on. We'll start out with 0, and then we need a node reference that is a copy of the head so we don't actually overwrite the head. Then let's go ahead and set up a loop to walk down the list until we reach the index we're looking for. While I doesn't reach is not equal to the target index, if we ever run into a case where the index we're currently located at is null, then we throw an index out of bounds exception, because we know that there's nothing here. Here, the state of our loop is that I is 0, and current is whatever is at index 0, and so if we stumble upon a reference that is currently null, and we still have more steps to go, then we actually need to throw that exception right away. Otherwise, we move one step forward by replacing the current reference with current.next and incrementing our I by 1. The outcome of that will be that I is incremented to 1, current is moved up to its next neighbor, and then now we have a reference to the ith index element, the ith index node, the 1th index node, so to speak, and we restart the loop. We exit the loop when I reaches the index. So the moment I equals index, the loop should complete, and then current represents the node at the particular index. One more thing you will have to do is one more null check down here. It may seem a little counterintuitive because we've already been doing null checks within the body of the while loop, but it is actually necessary in the case that current.next ends up being null. This avoids this null pointer lookup that we might end up doing if we just return current.payload right away. It's entirely possible that the index that we've reached ends up being null, but we only ever check the indices that come before it inside the body of this loop. So be careful there. It's kind of like an off by 1 error. Once we pass that guard statement and we've determined that current is indeed non-null and stores a value and is the index that we're looking for, we of course want to return the payload stored inside that node. It's a simple mistake to make to not return the payload but the node itself. Please be very conscious of the method signature here. The type we want to return is of course the value stored inside the node, not just the node itself. So we want to return the payload value within the current field and not just current. Okay, I don't think the get method poses too much of a challenge, but if it does to you, I do encourage you to try writing this method without help, without reference to existing materials, so you can get comfortable with that reference assignment, doing those sort of guard statements and null lookups or null validations, and being comfortable with essentially looping through this structure so that we can reach a reference within the structure without using just fast indexing that we got out of the array list. Okay, that's all I've got for the exam review materials. For the online exam, you can expect these exam problems to be a little bit more difficult than what you would see in these sample exam materials. The reason for that is for the sample exam, this exam was a real exam at one point that was taken in class. It was closed book and closed note and time limited, so I had to be conscious of the resources that students had. For the open note, open book exam that you're going to be doing online, you have access to basically everything. You can read official Java docs, you can read the class notes, you can rewatch the class lectures, you can use the help of an IDE, and you're still going to get the same style of question, but they might have slightly more difficulty and complexity than the ones you see here, which I think is a fair trade-off given that you essentially have unlimited time to take the exam and can check your answers on your own time. Okay, my cat's meowing. Thank you for listening. If you have questions, as always, please ask me on Piazza or shoot me an email, and I'll try to get back to you as soon as I can.